statements which define what measurement uncertainty is. I will start with a statement from the guidance of uncertainty in measurement. So it's not really standard, it's a guidance, but it's the basic procedure or the basic document which describes procedure of evaluating measurement uncertainty. And it says, in general, the result of a measurement is only an approximation or estimate of the value of the measurement, and thus is complete only when accompanied by a statement of the uncertainty of that estimate. That is, of course, true, but of course also very detailed, and we can sum that up or summarize that. And there is a professor, Professor Werner Richter from Leipzig University in Germany. He said, specifying a measurement result without indicating the measurement uncertainty is so uncertain that it is better not to specify it at all. Or if we even summarize again and we directly hit it to the point, then Dave Packard said, measurements are always wrong. It's just a matter of how wrong. So all of those are true, and we will now try to make these statements in words a bit more technical. And for this, in the first step, I want to show you, based on an example, why measurement uncertainty is such an interesting and important topic. Therefore, we start again with the measured quantities. As we just heard, all measured quantities contain a certain amount of measurement uncertainty. That's related to the fact that measurement processes are also influenced by environmental effects and conditions, and the environmental conditions can often be not controlled or not infinitely accurate controlled. And in addition to that, all measurement equipment, independent from the manufacturer, each sensor, each power meter, contains a lot of different components, and all have manufacturing tolerances. And independent from the level of quality, it is impossible to build up a really absolutely perfect system. And for those two reasons, each measured quantity contains measurement uncertainty. And if we now think again about our electric drivetrain, we measure voltage and current. Both of the measurements contain measurement uncertainty. And then we calculate energy, power, or efficiency from these measured quantities. And of course, the measurement uncertainty of the measured data propagates to the calculated data. And if we go now a step further to our vehicle application, then the vehicle, of course, one part of the vehicle is the battery with a defined and limited battery or energy capacity. And if we calculate the energy consumption of the car from our measurements, and we have measurement uncertainty in that energy consumption, then also the expected range of the car has a kind of measurement uncertainty. Or in other words, if we have a lower measurement uncertainty in voltage and current, this enables a higher range specification of our vehicle. And that is one example why a lot of our customers are so interested in this topic. Now, to go to the analysis and how to evaluate measurement uncertainty, I want to again distinguish between different error effects. In this context, I distinguish between two groups: systematic error effects on the one hand side, and these errors are characterized by the fact that they are reproducible if I repeat a measurement in the first step equal environmental conditions, but also, of course, with the same operating point. And then, since we can reproduce by following measurements these error effects, they are generally avoidable by compensation. And if we talk about measurement, this means calibration. And examples are, only to mention some environmental conditions which are not compensated for, such as temperature. Temperature affects, for example, the input amplifier, because resistances in the input amplifier are temperature dependent, for example. Or again, the manufacturing tolerances of passive components. And we have here a nice metaphoric picture, the target with bow and arrow. So if you imagine the side of the bow is mounted in the wrong angle, then you can shoot the arrow as often as you want, you will never hit the sender target. And that is a typical systematic error. And on the other side, we have random error effects. And these random error effects lead to measured values which scatter around the true value. And this is also the fact if we compensate the systematic errors and if we have the same ambient conditions, or let's say apparently the same ambient conditions. These errors are therefore unfortunately not reproducible, and we cannot compensate for it. And we can, in this group, again distinguish between kind of a, let's call it real randomness, which is related to quantum mechanical processes such as thermal noise or resistive noise. And we have, that is also an important one, apparently random, but actually deterministic processes. And they are characterized by the fact that the origin is unknown and they seem to be random. But in reality, of course, you could explain it by classical physics, but the model is too complex. If you think about our arrow again, for example, continuously changing wind conditions could be such an error because wind, weather, and also turbulences are deterministically chaotic processes. You can explain them by classical physics, but it's too complicated sometimes, and therefore a very small change in the ambient conditions leads to a very different measurement result. That's what characteristic for chaotic processes. And as you realize from this explanation, it's sometimes difficult to group the errors in one of these two groups, to separate it. And it's also possible that if we have an apparently random effect, that this may be transferred to a systematic error effect if we improve our model of the measurement process and then are able to explain the behavior and then also able to compensate for it. So this is not always absolutely separated, but it's important to treat it different. And with these two different kinds of errors, we want to talk about some other basic terms. So if we do a measurement, we typically do not know the true value. That's the reason why we measure. And if we then in the first step consider that we only have systematic errors and we measure and we do the measurement again and again and again, the measured value will, due to systematic errors, not be equal to the true value here, but it could be, for example, here. But if we're talking about systematic errors, for each measurement, the result would be here. But this is not what we know from real measurements. If we measure several times after another, then we will see that, of course, a lot or most of our measurements are very close to this expected value. But there are also some which are a bit more far away. And this is related to random errors. And we can model this by probability distributions. This is the red curve. In this case, as an example, it's a standard normal distribution. And the probability distribution defines the probability that the measured value is in a certain interval around the expected value. So for a standard normal distribution, round about 68% of the measurements are in an interval of minus to plus the standard deviation around the expected value. And if you would not have any systematic errors, which is not possible what in the last detail, but of course by calibration you can nearly achieve that, then the expected value is equal to the true value. And with this knowledge, we can now go to the error propagation, which means we measure some quantities and then we calculate others from these measured quantities. And if we know the error of the measured ones, how does that propagate to the calculated ones?